In this episode, we're going to be checking out Kubernetes, which is very popular for container orchestration. We'll chat about what Kubernetes is, why people are using it, and then look at how it works by deploying an example application to a test cluster. The Kubernetes site has a pretty good summary about what Kubernetes is. It says Kubernetes, or k8s for short, is an open source system for automating deployment, scaling, and management of containerized applications. But what does that actually mean? Well, let's jump over to our containers in production map for a second and zoom in on the container orchestration section. Container orchestration is really the heart and soul of your production deployment, as it will automate much of the deployment and scaling bits needed for running containerized applications. You can't go far without it. For this episode, I want to step back for a few minutes and chat generally about the concept of container orchestration and what that means, as most of these orchestration tools, even outside of Kubernetes, have these types of features. So it makes sense to chat about it in general and hopefully flush things out. I've created a few diagrams that will help explain what I'm talking about. So what is container orchestration? Well, let's mock up an example cluster here and then walk through a few scenarios. Imagine you have 3 servers. We'll call these master nodes. These are in charge of running your cluster. Next, we'll have a set of worker nodes. All of these machines will typically be running a fairly minimalistic operating system with Docker installed. Once they're configured, you'll typically not be doing anything on them except running containerized applications. I added the 3 master nodes and 5 worker nodes for high availability. The general concept is that we can have a few of these nodes fail and things will still be okay because we've built in redundancy. Also note, these master nodes are special in that they'll be coordinating what's happening on the cluster along with scheduling and monitoring container deployments. These master nodes are constantly chatting with each other too. They use tools like etcd, a distributed database, to share state and prevent one master node failure from taking down the whole cluster. You typically wouldn't run anything else on these master nodes except the software for managing the cluster. Basically, you're not putting workloads on there. The master nodes, besides chatting amongst themselves, are also constantly communicating with worker nodes to make sure things are healthy and running as expected. It might help to think of these master nodes as constantly tracking things like the status of all master nodes, the status of all worker nodes, and the status of all containerized applications deployed into the cluster. This state information is constantly replicated across the master nodes too. Now that we have our example cluster up and running with master and worker nodes, let's deploy an example application to it. You might say, hey, run 5 instances of my front-end container. To do this with Kubernetes, you'd typically use the kubectl command to connect to the master node and either pass in command line arguments or pass in a YAML file that describes your application and what you want to happen. You can also automate these steps with a continuous integration pipeline down the road too. These master nodes will do a bunch of stuff based off your request, if you're authenticated, of course. The master nodes look at the available worker node resources and start to schedule the deployment of your Dockerized application across the cluster. The master nodes will instruct these worker nodes to pull down the front-end containerized application and fire it up. This is indicated by these blue boxes being pushed out here. You notice that your application is automatically distributed across worker nodes in the cluster too, since we asked for 5 instances of our app to be deployed. But say, for example, that a few hours has passed and one of these container crashes on the center worker node here. The cluster will all of a sudden notice that it has 4 instances running, but you asked for 5. So it will take action to self-heal the application by starting another instance, so that it has the desired 5 instances. The cluster is constantly evaluating its current state against what is expected. This right here is what I think of as the general concept behind container orchestration. Basically, orchestration allows you to make the jump from running Docker on a single machine to running Docker on multiple machines without going crazy. Imagine trying to run 20 different application types, all with multiple instances across a bunch of machines. It would be near impossible to do manually. So this is why container orchestration tools like Kubernetes exist. Let's walk through deploying a few more applications and then chatting about the pros and cons. Maybe there's another group at your company and they want to deploy 3 instances of their backend application. Again, they pass the request via the kubectl command with a YAML file that describes what they want to the master nodes. Kubernetes looks at this request and schedules the deployment across the worker nodes. You will notice here that the red dots skipped a worker node. Kubernetes is constantly looking at worker nodes to see what their resources are like, and will try to pick what it thinks is the best worker for that workload. Most orchestration tools allow you to configure this though. Let's deploy another application. So you have an analytics group at work who are tracking application usage, and they're collecting tons of metrics. So they want 10 instances of their analytics web app deployed. Again, Kubernetes will schedule and deploy their containers just like before. Let's stop here for a minute. One of the really cool things about container orchestration in general is that you can take a group of machines and use them to run all types of different containerized applications. Before containers came along, I used to have sets or groups of machines dedicated to each type of application I wanted to run. Things like processing nodes, web servers, log processing, etc. Here, we take a single group of machines and easily deploy many different types of applications onto them. With Docker and orchestration software, you can greatly drive up hardware utilization. This can lead to big savings when you're looking at downsizing hardware. Also, what's cool about container orchestration is you're basically handing the day to day operations of your running applications over to this orchestration software. What does that mean? Well, before this type of software arrived, you'd typically have a sysadmin, me, who took all types of requests and would manually install and look after things. Or better yet, I'd use configuration management software. But still, I'd have to keep an eye on things. When things failed, like an application died or a machine failed, I'd get paged and I'd have to do something about it. With Docker, orchestration software, and the cloud, almost all these types of problems go away or become a lot less painful. It's just awesome. Let's explore what happens when a worker node has a critical failure. For example, the last worker went down hard and it stopped responding, but it was running some of our containers for our analytics and front end applications. Well, again, the master nodes are constantly checking the health of pretty much everything and will quickly notice that the containers have gone away and that the worker has stopped responding. The cluster will attempt to self heal, and it will look something like this. Analytics and front end are both having issues. Analytics should have 10 instances running, but I only see 7. Front end should have 5 instances, but I only see 4. Let's redeploy these failed instances to healthy worker nodes so that we can get our instance counts back up to where they should be. You'll notice that's pretty much the logic you'd take if you were paged at 2 a.m. too, which is pretty awesome that it happens on its own. You might be thinking, what happens if the cluster doesn't have the resources to accommodate this failover? Well, that's kind of a tough situation because the master nodes don't have the resources available to get the instance counts up to where they should be. So you'll typically see a bunch of log messages saying, hey, I tried to do this, but I couldn't. Please add more resources. So that's why you always want to have a bit of extra capacity in your cluster to accommodate these types of failovers. So just to review some of the pros of using orchestration software. One of the really big ones is it frees you up from the day-to-day manual work of doing this type of stuff. Personally, I honestly don't even know if I could manage all that complexity without orchestration software. We're not talking about small apps here. Mostly this is startups or enterprise type companies doing this type of thing. They have tons of apps and need to run them across lots of machines. This allows them to really drive up hardware utilization from where it is today without containers. Personally, I just love the self-healing aspect of it. I'd way rather have a system take corrective action and then let me know versus me having to do something. There's also sort of a hidden bonus here if you're using a cloud provider, in that the backend infrastructure can likely replace these failed worker or master nodes automatically. The cloud just totally allows you to reroute around hardware failures that you can't do if you're running your own data center. So you might be thinking, okay, you have these apps running on the worker nodes, but what about networking? Well, I conveniently didn't mention that because the diagrams are already pretty packed. So let's cover that now. I'm just going to move things down here and hide the master nodes while we chat about this. But we still have our worker nodes running our 3 different types of applications. In general, things work like this. After you ask the master nodes to deploy your application, you'll also ask the master nodes to deploy a software-defined load balancer. Let's look at our analytics application, for example. We originally asked for 10 instances of our analytics software to be running in the cluster. The instances were spread across 5 nodes, so we need a way of routing traffic to them. The software-defined load balance service basically sits in front of all your application instances. Typically, there will be some type of label or flag that the load balancer will look for on your instances. This is important because you can easily scale up and down your application instance count, and you want the load balancer to pick up these changes. The load balancer is also mapping external requests to the various internal IP address and port numbers of your containerized application instances. So let's deploy a load balancer for our backend and front-end services too. I should mention that there are way too many options here. You have HTTP load balancers, TCP, and UDP. It's highly dependent on the orchestration software you're using and where you're using it. For example, if you're using Kubernetes in AWS, your options will be totally different than running Kubernetes on bare metal in your colo. This is a pretty massive topic, so I'm totally glossing over a lot of the details and talking in general here on purpose. Having said that, I'd like to do a few episodes on common configurations and sort of walk through a few examples and do some demos, but we're not going to do that today. Okay, so we have our analytics, backend, and front end applications all sitting behind non routable internal cluster addresses. It's all wired up, but how do we route traffic from the internet to these non routable addresses? Well, I'm going to give the cloud provider example here because that's what I'm going to do in the demo later. Basically, you'll create a cloud load balancer, something like a AWS Elastic Load Balancer or a Google Cloud Load Balancer, and then route traffic from this cloud load balancer to your Kubernetes load balancer or whatever orchestration tool you're using. Then we'll do that for the other two too. I added these host names here so you can sort of logically follow the flow. You have a host name that's pointed at a external cloud load balancer IP address. That cloud load balancer is pointed at your orchestration load balancer, and then traffic is routed into your cluster. This seems a little complex, but it actually works pretty well. Honestly, though, there's so many options. If you can imagine it, you can probably do it. So I'm not going to get too concerned about it here. Cool. So that's it for the diagrams. Hopefully you found that useful. So let's move on to the demo section where we put this into practice. For the demo today, we're going to configure a test cluster using Google Cloud's Kubernetes engine. It's a pretty easy tool that allows you to spin up a Kubernetes cluster in just a few minutes. I just wanted to highlight that it's fully managed. Google even looks after the master nodes for you without charge, which is pretty cool. Google also manages the OS and deploys rolling upgrades for you. This isn't an ad or anything, or it's sponsored. Sure, I'm biased, but it just works really good for demos and that you don't need to do any crazy stuff. Cool, so let's log into the console. Oh, if you want to play around with this, I think new customers get a $300 credit. All you need is a new Gmail address that's never signed up to Google Cloud before. So this is what the default console looks like. Let's go to the left-hand side here and up to the hamburger menu icon, and then select Kubernetes. This might look different for you if you give it a try. I use Kubernetes quite a bit, so I've pinned it up top here. This panel lets you create a new Kubernetes cluster or review your currently running clusters. I don't have anything in this account, so let's create a new cluster by just clicking Create Cluster, and it'll open up a wizard. On the left-hand side here, there's a bunch of templates that you can use, but I know the values I want, so I'm just going to use them. I'm just going to leave the default name as it is, since this is a test cluster. I'm going to leave it as zonal versus regional. You could use this to say spread the cluster across multiple data centers so that, a failure in a particular data center doesn't take your cluster down. Then I'm going to pick US West 1 as that's a data center close to me. You can also select the Kubernetes version you want, even though it's a managed offering from Google. Say you wanted to test out a new feature or something, you can do that here. Here's where we get to select the amount of worker nodes that we want. It's set at 3 right now, but I'm going to choose 5 since that's what we were chatting about in the diagrams earlier. Finally, let's click Create. From what I've seen, it typically takes about 3 to 5 minutes to spin up a new cluster, but I also think it depends on the amount of worker nodes that you're using too. While that's going, I should probably tell you what the demo is. I created an example application here and uploaded it to GitHub. Basically, it's a website that prints out the host name of the container running that instance. So the idea is we can scale up our application to something like 10 instances, and then we can verify things are working. I kind of like these simple sort of end-to-end tests in that it proves, hey, we have a cluster running. Hey, we have instances running. Hey, the internal service load balancer is up and our external cloud load balancer is also serving traffic. So this simple test sort of proves a bunch of things. I also created a live demo of this, which you can check out. It's called sysadmindemo.com. Our plan is to sort of hang a bunch of demos that we create off this domain. So you can see the container host name that served this request right here. And then if I refresh the page, this host name gets updated. I'll just refresh a few more times here. This basically proves we have a working end-to-end solution. All right, let's jump back to the cloud console and set up our demo. Great, the cluster looks ready now. You can use this connect button to pull up a command prompt where we can authenticate and then run commands against the cluster. I'm going to choose Cloud Shell here. This is basically a web-based command prompt sitting in Google Cloud. And I like to go full screen on it. Okay, so we have our first command here. This configures authentication and points our kubectl command at the correct cluster. Say, for example, you had 5 different clusters, so you need to make sure you're pointed at the right one when you're running commands. I showed you the demo already, and I showed you what the GitHub page looks like, but I don't think I showed you Docker Hub. So let's jump over there. Basically, this is the Docker image that I built using the code that's up on GitHub. I just wanted to show you this so it all makes sense when I'm running the command. You're thinking, hey, where did you get this image from? All right, so we're going to say kubectl run demo. That's the application name. And then we're going to provide the image. And then I also want to tell Kubernetes the port information. This is the port our web server is running on inside that Docker image. I just like to verify things too. So let's run kubectl get deployment demo. Awesome. So we have one instance running, but we can scale that up later. I don't think I showed you the worker nodes yet. You can also get a list of them by running kubectl get nodes. And then you can see our 5 worker nodes here. So you'll remember back from our networking diagram where we needed to configure that software-defined cluster load balancer for our service. That's what we're going to do here. Let's run kubectl expose deployment demo, and then we'll say the target port, and then we'll say type node port. Again, let's verify this by running kubectl get service demo. Awesome. You can see our cluster IP here. That is fronting our demo service. Let's just quickly recap by looking at that diagram again. So we have our worker nodes, the instance is running, and we've configured the cluster load balancer that is fronting that instance. Although we only have one right now, but we can change that in a minute. So the next step would be to configure the cloud load balancer that connects to our Kubernetes load balancer, sitting in front of our demo application. Let's do that with a YAML config file this time. I'm just going to create the file called basicingress.yaml and paste in the contents. Since Kubernetes has deep integrations with Google Cloud, you can create external load balancers right from within Kubernetes like this. We're saying here, create an ingress load balancer and send traffic to our demo load balancer application. Now let's apply that change to Kubernetes by running kubectl apply -f. This says, hey, we want to send a file over, and then basicingress.yaml. We can verify things by running kubectl get ingress basic ingress. We should see the external load balancer IP address here in a minute. Great, this is our external IP address, but don't get too excited just yet. From my testing, it takes about 10 minutes for this to fully come online. So we can hit this address, but we'll just get a 404 error until traffic is finally directed into our cluster. Maybe while we're waiting for that to happen, we'll scale up our application from 1 instance to 10. Let's check the current state again by running kubectl get deployments. All right, you can see our demo application only has 1 instance running. So let's run kubectl scale replicas 10 deployment/demo. And then again, verify. Awesome. Looks like we have 10 instances now. Let's go back and refresh that external load balancer again. Yeah, it's not up. It's going to take about 10 minutes. So what I'm going to do is I'll chop the video. I'm going to stop it now, and then I'll come back in a second. All right. And through the magic of video editing, it's now live. I just chopped about 10 minutes out of here while we were getting that set up. And you can see if we refresh the page, the host name is changing. And we can verify it's our cluster too by taking note of this host name. So let's just remember the tail end here and then flip back to the command prompt. And if we run kubectl get pods, you can see a list of our pods and the host names that they have. So, hey, we found our instance right here. So let's go back to the demo and hit refresh a few times and get a new host name. Awesome. So just take note of this one. And then let's flip over to the console again. And hey, we have a match. Cool. So this basically proves we have a working end-to-end setup. Obviously, there's way more to Kubernetes than just this, but hopefully this sort of lays the foundation for where you can go in the future. Before I delete the cluster, I just wanted to show you some of the web UI that Google Cloud provides around Kubernetes Engine. So if we flip back over here, you can actually see there's metadata about how many nodes, what the versions are, all that kind of stuff. The real kind of cool stuff is if we go under workloads, you can see, hey, here's our demo application. You can pull up things like histograms, what pods are running. You can pull up logs, any event logs, the YAML files, all that kind of cool stuff is readily available just in the UI. You don't have to go fishing through the command line, which is actually pretty cool. Cool. I'm going to delete the cluster now. And that's it for this episode. Thanks for watching, and I'll see you next week. Bye.